Okay. Okay, so let me just do a quick introduction. Today, the diiP is very happy to welcome Professor Gerd Gigerenzer for our distinguished lecture series. And just a very, very quick overview. Many of you, with the invitation, you got the quick bio, but I will just repeat some of the things. Professor Gigerenzer spent the early years of his career in Germany and Austria at the universities of Munich, Constance, and Salzburg before becoming professor of psychology in 1992 at the University of Chicago. He then became, in 1995, director of the Max Planck Institute of Psychological Research in Munich and the Max Planck Institute of Human Development in Berlin. And since 2009, he is director of the Harding Center for Risk Literacy in Berlin and later Potsdam. And in this role, as far as I saw on like more general news, he also consulted or consults German government-related institutions in crisis or risk situations, such as, for example, the COVID pandemic. And Professor Gigerenzer investigates how humans make inferences about their world with limited time and knowledge. And in a data-rich world with high levels of uncertainty, how humans handle the big data crunching that we do in many of our projects at the diiP, or whether they do this big data crunching in any at all. And actually, I thought that Professor Gigerenzer would be a great addition to our lecture series when I recently came across his book, How to Stay Smart in a Smart World, where he discusses some of the problems that we handle. We discuss quite a lot about fair AI and transparent AI. I think I just give the floor to you. And thanks again so much to be here and present your work. Thank you so much.
Yeah. How does one make good decisions? The traditional answer is rational choice theory, which basically assumes that we know all the future possible states of the world, all the consequences, and also the probabilities. That model has since long dominated economics, decision theory, and much of psychology. Herbert Simon was one of the first who provided an alternative. He called it bounded rationality. Bounded rationality was a revolutionary program, and I'll in a minute explain why. And what happened to his revolution was that it has been sidetracked, and bounded rationality has been reinterpreted, given a new meaning that he never wanted, and actually two. The first one was, namely, that bounded rationality is nothing than optimization under constraints. It is basically reducing bounded rationality again to maximizing expected utility, for instance. In personal conversation, he once told me that he considered suing authors who misuse his concept on that. But that was not the only misinterpretation of his concept of bounded rationality. The second misinterpretation was something like the opposite, namely that bounded rationality is irrationality. And that was mostly featured by psychologists, such as in the heuristics and biases program, where bounded rationality was reduced to deviations from optimization models, in particular, maximization of expected utility models. So I will start now first to explain what he really meant, and then introduce you into the science of ecological rationality, a term that my research group and I coined in order to get bounded rationality out of the ether of the irrationality or of the optimization under constraints misunderstanding. So, and then I will give you a few examples about how to get a better idea about the nature of human intelligence, and also how one can be smarter than rational. So that's the program. And if you're ready, then we'll start. So let me first explain what Simon's bounded rationality means and why this is a revolutionary program. It can be defined by three principles. The first is one, model what people actually do. That means their actual decision process, not just the result, and not as if utility maximization. So for economists, utility maximization is as if, because they don't care what people really do. It's a kind of anti-psychologism that's usually by the term behavioral, such as in behavioral economics has survived. Or now it's behavioral sciences. And it's, yeah. So the first one is take care and study how people, including experts, actually make decisions and model the process. The second principle is uncertainty. Model decisions under uncertainty, not only under risk. Now, the terms uncertain and risk are commonly misunderstood, and this is why I brought you an entire definition here. And I use Savage's concept of a small world to get that. So a small world is a situation where a decision maker has a perfect foresight of all possible future states. Precisely the exhaustive and mutually exclusive set S of all future states of the world. And also perfect foresights of all the consequences. That's called a small world. Small worlds exist, such as if you play the roulette, you know all possible future states. It's the numbers, and including 0, and you know all the consequences and the probabilities. The same with lotteries. And much of studies in cognitive science are modeled after that small worlds where the experimenter knows what's the right answer is, and subjects can just fail. So a small world is about certainty, including certainty about the probabilities. If the probabilities are not known, it's called ambiguity. If they're known, it's called a situation of risk. Okay. And much of the problems that we study in psychology, from experimental games to the trolley problem, to choices between monetary alternatives, are all problems in small worlds. Whether the results generalize to the real world, that's completely unclear. So the term uncertainty refers to all situations that aren't small worlds. That means if you don't know all future states, or if you don't know all the consequences. For instance, if you have to decide which one of 2 job offers you take, you aren't in a small world, only if you're in a psychological lab where you're told what the consequences are. If you want to find the right romantic partner, you have to do it with lots of uncertainty. And also, there are situations that are called intractability, where decision theory also doesn't apply because the state is too big to find the optimum. So it's important to keep these terms apart. For instance, in classical decision theory, the term ambiguity is often used instead of uncertainty, and then no uncertainty exists. Or in the Heuristics and Biases program by Kahneman, Tversky, and others, it's called judgment under uncertainty, but the examples are all about risk. The researcher knows what the right answer is. In the real world, we mostly don't know. We don't know how the coronavirus will develop. We don't know what's the best thing to do about the war in Ukraine, but still we have to make the decisions. And that's the topic of bounded rationality. So the third one, principle is model the match of the mind, so the mental process, to the environment. And this is equally revolutionary because most of cognitive science is just about the mind. So concepts like risk aversion or theory of mind or system one are all just about the mind. There is no environment in the theory. Economics, on the other side, just looks about incentive structures and the environment. Or Skinner theory is all about the environment. Simon's idea was to get to a theory that really asks the question, so which mental heuristic works in what environment? And that also has a practical side, how to design the environment so that humans easily understand and can make quickly good decisions. So that's the program of the study of bounded rationality that I call ecological rationality. It has three types of questions. The first one is descriptive. What's in the adaptive toolbox? So it's a toolbox. It's not one tool like Bayesian probability updating. It's not one tool like expected utility maximization. The mind needs more tools than one. But many researchers have the desire to have one tool for everything. That's Leibniz's old dream, that he could find a calculus that solves all our problems. That's a beautiful dream, it's an illusion. So the question here is, what are heuristics we use, the building blocks, and the evolved capacities they exploit? So heuristics can be social heuristics like tit for tat, or imitate the successful. They consist of building blocks, and they need the evolved brain to actually be able to work. So, as you know, Mike Tomasello, for instance, has studied human infants compared to chimpanzees, and one of the key differences is a heuristic, namely the human capacity to imitate. And children imitate much more consistently, broadly, and precisely than chimpanzees. So that's the first question. What's in your adaptive toolbox or in the adaptive toolbox of an entire culture? The second question is new. It's a normative or prescriptive question. In what environment does a given heuristic work? While the first question, adaptive toolbox, is about observation, experiments, and other empirical research, ecological rationality is dealt with mathematical proofs. And I'll give you an example, or computer simulation, if you're not smart enough to find proofs. And finally, there's an engineering component, namely use all these results to do better design so that people of the environment, for instance, that people can make better decisions, and also to inform the design of algorithms. Machine learning today is a statistical discipline. If you read machine learning books, it's an introduction to statistics. And psychology plays little, if any, role. I think it's an error to throw everything aside what the human brain has evolved. And if you are in a world of risk, or more generally, a stable world, a well-defined one, then you don't need psychological AI. You just do statistics, like in deep artificial neural networks. And that's the place where these networks really work. Games like chess and Go, industry applications, and everything where the future is roughly like the past. If that's not the case, then big data wouldn't help you. It actually can mislead you. I'll give you one example. So the key program is there's a descriptive component, a prescriptive, and an engineering. And I'll give you just a few examples for that to illustrate this principle. So let's consider hiring. So how to make a decision about hiring. And although in rational choice theory, you would basically have all the information about all the candidates and choose the one with the highest expected utility. Good luck. We know that experienced professionals do everything else. And as Simon found, rational choice theory, as he said, useless in the real world of budget planning, for instance. So it doesn't help you really. I give you one class of heuristics that we call one reason heuristics, which are very interesting because you reduce the entire search space to one reason. When Tesla was still a small company and Elon Musk made the hiring decisions, he reported how he did it. And here's the model of what he did. The model is very simple. It's one question. Does this candidate possess some exceptional ability? If no, no hire. If yes, hire. Now, how does he find out that the person is not lying? No. Musk asked questions like, tell me about some of the most difficult problems you worked on, how you solved them. And he was looking about a cue that also psychological research has identified as the most powerful cue is whether the report given to him by the candidate is detailed. If not, it's probably a lie. So it's basically heuristics all the way down. And many of these heuristics work unconsciously. So the adaptive toolbox contains this type of one reason heuristics. Now, these heuristics are usually misunderstood as something that are due to cognitive limitations or to laziness or just any kind of biases. And in the heuristics and biases program, you will find a kind looking down at all these heuristics that because they're not doing expected utility maximization. That's not true. It's a misleading conception. Under uncertainty, less can be more. And the study of ecological rationality poses now the question, can we identify a certain environments where relying on one good reason cannot be beaten by a standard class of complex rational choice algorithms. And I'll give you one intuitive example where you can easily, in a few seconds, see, and no big proof is needed. So imagine a situation where you have 5 queues, not just one, as Musk had. And the queues have weights. So let's think about this from a linear perspective, like a logistic regression or as a kind of regression. The weights, each weight is the additional contribution to the queue before. So in statistics, that would be called beta weights. So now, A dominant Q situation is the following. If the weights of the first Q, if the weight of the first Q is larger than the sum of the remaining weights, as shown in this illustration. In such a situation, you can prove that a one reason heuristic that only focuses on Q number one cannot be beaten by any kind of additional Qs. Actually, you're better off ignoring them because there's another component in the complex models, because they come better. They have free parameters and they may overfit and actually worsen everything. So that's an illustration that less can be more, and we can prove the situation. And when one looks in typically machine learning repositories of data and analyzes whether this condition holds, you will find a surprising large number of actual data where this condition holds. And intuitively, you can see if you have a situation where the predictors or variables or Qs are highly correlated, that's exactly this situation. For instance, when doctors look at symptoms, they're typically correlated, and you get in this situation. And that's why a doctor who has experience can, in a glance, often know there's something wrong and it's going on. So let's move on. One reason heuristics, which have one clever Q, are not the only class of heuristics. Here is another one. When Amazon was still a small company, Jeff Bezos also made his own hiring decisions. He used not one Q, but up to 3. And from his own reports, we have modeled that by a fast and frugal tree. A fast and frugal tree is a tree that's incomplete and has, so in this case, 3 questions and 4 exits. It has on each question an exit. And that gives it possibilities that full trees do not have. It's not just a small version of a full tree. It can actually deal with uncertainty. It can deal with intractability and can deal with incommensurability. So Bezos was asking, interestingly, the same question as Musk. Does this person possess some exceptional ability? If no, out. If yes, not enough. Then he asked a second one, will you admire this person? Very unusual, but Bezos thought, if he can admire people, he will learn from that. If no, out. Otherwise, a third question is asked, will this person raise the average level of effectiveness in the group they are entering? And if yes, only then the higher. And the logic is also clear here. The last question makes sure that the level of effectiveness is constantly rising with each higher. So that's a fast and frugal tree. And it can deal with uncertainty in the sense there are no probabilities involved here. You don't need to know only consequences, only the most important one. It can deal with incommensurability. So in standard decision theory, you need a common currency because you have to weigh them and add them. Here, that's not needed. You don't have to say how much exceptional ability is worth admiring a person. And it makes no sense in the first place. You only need an order. So these are mathematical structures that go with order, that do not need compensation. And it also can deal with intractability. A decision tree, a full tree that has many of these variables gets quickly intractable. And that's the problem of Bayesian decision theories. trees. So now, how to analyze these trees and study their ecological rationality? I give you just one example. So the Bezos tree has a specific design, and there are other trees possible. For instance, if you have the same 3 variables in the same order, then you can get 4 trees. And when you make a decision, you can commit 2 errors. You can make, in this case, you make an offer to the wrong person. That would be a false positive. Or you can make no offer to the right person. That would be a miss. And the Bezos tree is the one on the left side. And you can see, no higher, second question, no higher, third question, no higher, is avoiding false positives at the cost of misses. On the right side, you see the other way to design such a tree. You always have a higher, only in the case none of these 3 Qs are satisfied. And the interesting trees on the middle, and they're not as easily to put into a logical order, where you have a compromise between those. So the point here is the trees can be designed in a way to have a compromise between the misses you can tolerate at the cost of false alarms and the other way around. In decision tree theory, these compromises are on a so-called receiver-operator curve, and you can map these trees exactly on 4 points in the ROC curve. And you can read more about that if you're interested. I use this as an example for the third use of the study of ecological rationality, namely intuitive design. Intuitive means it's based on what people actually do, as opposed to as if expected utility maximization or prospect theory, which is another as if model. And it's systematically designed based on data and order based on considerations such as what's more important, minimize misses and false positives. I'll give you now an example of a use of intuitive design in the real world. In my work with the Bank of England, the problem is, how can a central bank recognize a bank that is in a vulnerable condition? And as you may know, and I'm not going too long in this, there are Basel II and Basel III regulations that ask banks, for instance, to calculate a value at risk. If you calculate a value at risk, you need to, a large bank has maybe thousands of risk factors, which they correlate, and then you have to estimate a matrix of covariances that is in the order of millions. That borders on astrology. You're not able to reliably estimate that. And the result is that none of these methods, which get more and more complicated, has ever prevented a crisis. I've spoken to for instance, to the European Central Bank in my work with the Bank of England, and said, what you're doing is borders on astrology. If you think anyone would have said no, they know, but they don't know alternatives. They're mostly economists. So what's the alternative? Is to use psychological AI. So take seriously what the human mind does. So, and this is one of the classes of heuristic that we find in many areas, and not just with Jeff Bezos, and use a structure that is not about adding and weighing, but about order. And here, the first Q is, does a bank have a smaller leverage ratio than this number? So for instance, if that tree would have been used before the financial crisis of 2008, the Swiss bank UBS, that had to be saved after the fact, would immediately have gotten a red flag, despite it would have satisfied the other two criteria. So these trees, unlike full trees or Bayesian decision-making or expected utility maximization, don't make trade-offs. If you fail on the first one, that's it, and you can compensate it. This is very much a thinking like the human body works. If your heart fails, a good liver doesn't help you much. But almost all of decision theory, including cognitive theory, assumes compensation. And the reason is not because that's what the human mind does. The reason is because you can map this in a smooth utility function. This is a lexicographic structure, and you cannot map this in a utility function. But mapping into utility functions should not be the criterion to understand what humans do and what they should do. But we make this error constantly and try to represent everything what people do by models that assume such a mapping. If you want to know more about how to build fast and frugal trees, I can recommend you our book called Classification in the Wild, because classification is what these trees do. And that is a book that compares machine learning techniques, such as random forests, with fast and frugal trees and similar heuristics, and shows situations where complex machine learning techniques outperform simple heuristics, and also situations where a fast and frugal tree outperforms a random forest. And at the end, and also the focus is on ecological rationality, to understand the situations where complexity pays. And to make it simple, complexity pays in a stable world. This is like a small, savage's small world. If you have uncertainty, if the future is not like the past, then big data doesn't help. It misleads you. And that's I give you a concrete example now about the latter situation. Remember that Google engineers tried to predict the spread of the flu. And the flu virus is like the coronavirus one that is full with surprises. It doesn't build a stable world. Nevertheless, Google engineers bet on big data and complex algorithms. They basically were looking for analyzing about 50 million search terms to find those that correlated best, and tested hundreds of millions of possible models and selected the one that predicted best. The unusual thing about this situation compared to many other machine learning situations is that they are not doing data fitting, they're not doing out of sample prediction, but they're doing out of population prediction. That means real prediction about the future. You're not taking a data set and divide it in two and then fit your model on one and on the other side. This is a real prediction that's much more harder. So, and Google flu trends would have worked if the flu and also the humans who put in the search terms would be create a stable world. As you may remember, it ran for about 8 years with several updates, and at the end it was closed down. the hype that was at the beginning in the media was not repeated at the end. And this is the same thing as happened with IBM's Watson, was hyped. Watson for oncology is now it's now sold off in parts, and the media don't report about it. It's the same issue. And so what's the alternative? If you want to predict the flu next week, for instance, as Google Flu Trends did, so how, and you now think about psychological AI, you would ask yourself, how do humans deal with such a problem? And we know from memory research and also from decision research going back to 1838 to Brown's Law of Recency, that people ignore the far past and only use the more recent past. In the extreme, the recency heuristic says you just rely on the most recent data point and ignore all the rest and predict that next week's flu, so the flu-related doctor visits will be the same as last week's. So just last data. This is much easier. It doesn't need any 50 million search terms. It doesn't need to waste money on hundreds of millions of models and test them and update them, make them more complex. But how well does this fare? Also note, this heuristic is on the list of biases in the heuristics and biases program. And people say that because people, also researchers say that because people commit this recency fallacy, they need to be nudged into better behavior. This is a big error. The ecological rationality question is in what situations is it likely to work and when not? And under uncertainty, here's the result. What you see here is on the y-axis, the percentage of flu-related doctor visits. That was the criterion being predicted by both the recency heuristic blue and Google Flu Trends 8. On the x-axis is the entire 8 years of prediction that's being made. What you see is here, think about 2009. So 2009 here means January 1st. And in 2009, something unexpected happened. The swine flu hit, and it hit out of the season in the summer. Big data had learned the flu is high in the winter, low in the summer. And you can see here that consequently, the red curve, that's Google Flu Trends, underpredicted over months, and it couldn't adapt. And the Google engineers had to update it. The recency heuristic that doesn't relate on big data and quickly adapt to a new situation and go with it, doesn't commit that. The interesting thing is, what did Google engineers do when they witnessed the failure of their algorithm? They updated it, but how? There are basically two possibilities. One is, you have a complex algorithm, you have a complex problem, it fails, the algorithm, so what do? You make it more complex. That's what the Google engineers did. And they increased the number of predictors from 45 to about 160. Our research on based on insights from psychology show you that you need to go in the other direction. If a complex algorithm doesn't work under uncertainty, then make it simpler and not more complex. And that's the recency heuristic that's shown there is the most extreme simplification that you can think. So that's and if you look at this, the entire 8 years, the recency heuristic outperformed the big data in every year and for all 3 updates. On average, across the entire 8 years, it reduced the error by roughly half. And this is a case where under uncertainty, you can show that one data point can predict better than big data. That will not happen in a stable world. If the flu would be a well-behaved thing, then go for big data. If not, it's an illusion. So let me now give you a general idea why people use heuristics and why this is a good thing under uncertainty. So the human mind evolved to deal with situations of uncertainty, not risk, and not small worlds. It wasn't confronted with lotteries and roulette games, but with unpredictable behavior that usually comes from other people. The common answer to this question is the so-called accuracy-effort trade-off. That means if you reduce effort, such as make a heuristic, use a simple heuristic, then you lose accuracy. You just have seen several examples showing that this accuracy-effort trade-off is incorrect. It is only correct in a stable world, such a small world. It is not correct under uncertainty. Nevertheless, this is still the standard methods that you get in classical books, or if you read Kahneman, Thinking Fast and Slow. And the underlying way to think is that the total error you make, say, if you in prediction, is composed of only two candidates. One is bias and the other is noise. Noise is here kind of irreducible measurement error. So then the fiction is, if you reduce bias, that's the goal of the mind. And that's incorrect. Under uncertainty, it's not an accuracy effort trade-off, but a so-called bias variance trade-off. The bias variance trade-off is well known in machine learning and in statistics, but not well known in psychology, cognitive science, and economics. Here, there's a third component that's called variance. Variance is roughly what psychologists call overfitting. And sorry, let me explain it. If you have a number of samples from a population, each sample will give a different estimate. And the variance of this estimate is what this variance components is. If you have a simple heuristic that has no free parameter and doesn't rely on these estimates, as you have just seen, the recency heuristic, there's nothing to be estimated. You just look up the data from the CDC or other source. Then you reduce the error due to variance to zero. And heuristics have in general either zero parameter or only a few, and that's the advantage over there. So the real problem is not to reduce bias to zero, but to have a sufficiently small bias, but not too small, so that the variance doesn't increase. You can reduce bias to almost zero by having using many free parameters, and that's often where cognitive models are going. But then you can fit data well, but that doesn't mean you can predict well, as you have seen. So that's the general idea behind that, and it also explains why under uncertainty, simple heuristics that are adaptive are not the source of error. They actually make a reasonable trade-off between variance and bias. Let me slowly come to an end. There are three important methodological principles in this study of ecological rationality. First, you need formal models of heuristics, otherwise you can't prove anything. We have had for years vague labels such as availability, which has meant half a dozen different things, representativeness, or even labels like system 1 versus system 2, which are the nadir of psychological theorizing. You can't make any predictions. You can explain everything after the fact, or almost everything. That has become clear to many, including to those who have proposed that things. So make formal models. And that's very easy. A fast and frugal tree is a fast formal model, for instance. Then second, we need competitive testing, not null hypothesis testing. We need to test our pet model against the best competitors, not against the null. And that's usually done in machine learning, but it's still not done in much of psychology. And finally, we need tests of predictive power instead of data fitting. We have still, so there's a survey in the year, at the beginning of this century, the majority of psychological models that have been tested were tested only through data fitting. And then you always had complex models who do better, but it's a mathematical truism. You just add more free parameters, you fit better. The real test is in out-of-sample prediction. That's what machine learning typically does, but also in out-of-population prediction. That is real prediction, as in the flu case. And that's even more difficult than out-of-sample prediction. But in out-of-sample prediction, you create an apparently stable model, at least a population from which you randomly draw. That's not the case in out-of-population prediction, in real prediction, where surprises can happen, like the swine flu. So there are three misconceptions. Rationality is maximization of expected utility, only in small worlds, and they are rare. People use heuristics because they are lazy or irrational. That's a total misunderstanding. The human mind isn't so stupid as it's being portrayed. And there's a good reason why people use heuristics, and outside of small worlds, you have no choice but to use heuristics. The only question is, use those who are adapted to the situation. And finally, more information and more computation is always better? No, it's wrong. Under uncertainty, that's not the case. You increase your estimation error if you go after this. Yeah? So here's my summary. I've made a distinction between situations of risk and uncertainty. So risk is a special case of a small world. Uncertainty is a case of a large world. And these demand different types for making good decision making. On the one hand, logic and statistics is sufficient, but under uncertainty, it needs smart heuristics. A heuristic is smart if it's used in a situation where it's ecological rational. And ecological rationality is something very different than logical rationality. Logical rationality is about consistency, about axioms, about expected utility, maximization of Bayesian updating. All these models only work in small worlds, not outside. If you don't have if you don't know the full state space, you can't construct a probability distribution, not even a subjective one. That's often overlooked. Ecological rationality is about success in the real world. You find out whether a certain strategy or heuristic actually is better than another one. And then a fourth principle is less is more. The Bayon's variance dilemma gives you a mathematical foundation of it. The idea that heuristics would save you time, but you have to pay for accuracy, is still not true in the uncertainty. And finally, while many researchers try to get rid of uncertainty, even if they just give it a different name, uncertainty is, in my opinion, the driver of intelligence. If we would live in a world that's absolutely certain, where we would know the future, intelligence would have never evolved. We wouldn't need it. Also, emotions would have never evolved. Just imagine that the world would be certain. The future would be certain. We wouldn't need hope. There would be no disappointment. There would be no joy. We wouldn't need anything of the emotions. And there would be certainly no innovation possible. And if you are interested how these concepts apply to the world of AI, then here is a book that just came out. And here I make the same distinction between situations of stable worlds and not stable worlds. And I argue that self-driving cars, that means level 5 cars, will not be on the road. And I take any bet with you on that. The problem is there's too much uncertainty. Something else will happen, namely we have to adapt our environment and our behavior that needs to be more predictable. Level 4 cars are very likely to happen, but that means to redesign cities and to not allow human drivers on the road. That's much more interesting, much more deeper than the gimmick of self-driving cars. And here are many parallels where, in my view on AI, is coming out from decision theory and from heuristics, and also the idea that in situations where pure machine learning is not sufficient, think about psychological AI. There's a reason why human intelligence evolved, and it evolved to deal with situations under uncertainty. And here, machine learning, if you bring together machine learning with the psychology, then one can actually make computers smart. Thank you for your attention.
Yeah, thank you so much. This was really inspiring, I think. So I would just suggest that if you have a question, just raise your hand and we'll just let you activate your sound. You activate your sound. Is there? Oh, Frank Ramu. Yes, go ahead. You can just, yeah.
Yeah, hi. Thanks for a very interesting talk.
Hi.
So your point is quite convincing. However, you do emphasize that the heuristics that we have are relevant in a certain ecological context. And of course, the problem is that our current environment is quite different from the environment in which they were adaptive. So what would you say about our ability to navigate our current environment? You didn't address that in your talk.
Yeah, so it is true that heuristics evolved originally in a very different context, and that can lead to problems. And that's the same situation as we agree for sugar and salt, which weren't available then. Yes, but also we can learn to use heuristics. They are not like instincts. So you can learn to look at how hiring decisions are made and try your own heuristics, and you have to adapt them. Also, for instance, think about the first Q in Jeff Bezos and also the only one in Elon Musk's one. Exceptionality. That's important at the beginning of a business, of a startup. But at some point, you need to hire people also who have something different from exceptional abilities, who do the routine task. That means one has to adapt the heuristic to a changing environment. And that's the meaning of adaptive toolbox. Yes, but the point is, to realize that these tasks are done by heuristics and then analyze what are the best one in a situation given. And that's then the study of ecological rationality. Does this answer your question?
Yes, to some extent, if I may follow up.
Yeah.
I'm also thinking of decisions that people have to make that are very multidimensional.
Yeah.
Where you have to take, like, if you want to choose the right flat, the right flat to buy, or the right person to marry, there are many different considerations to take into account. These are very complex choices for people. One potential method to handle it is like to list a whole series of criteria and then to tick each of them for the various options. This is one possible way to handle multidimensionality when you can't hold all of the dimensions in your working memory. Does that sound a good heuristic to you, or would you still argue for much more simple heuristics based on a much more limited number of dimensions?
Yeah. So your argument is a very good one about multidimensionality. There could be a multidimensionality in the variables. There could be a multidimensionality in the criterion. If it's in the variables, a lexicographic heuristic takes care of it. It orders, and you don't have to make any trade-offs. If it's in the criterion, so you have multiple, which is often the case, you have to satisfy, or even worse, as you indicated at the beginning of what you said, if we will not know whether we have no real criteria. So take your example of a partner choice. So finding the right romantic partner. How do you find out that it is? And after 5 years, it may look different. And after another 5 years, again, different. So there are situations where it is very difficult to measure the success. But then there are other criterions at the same point. We are not just making decisions to reach a particular criteria, but multiple ones. For instance, there are observations that many men, when they choose the right wife, are not actually much looking at the person, but they're choosing the one that their friends desire. That's an old observation, and I stay there. So just as an example, and where one just goes about multiple criteria, and a heuristic can deal with that. And there may be situations where you never will find out. And the same is with hiring. You can have a criterion, how is the person after 1 year, but does this predict how it will be of 2 or 5 years? So there's still uncertainty, even in what the criteria are. Again, we can do something. We live our lives under this uncertainty. And my interest is to find out how people do this. And they're certainly not maximizing some expected utility.
Okay, thank you.
There's a question in the discussion. Actually, 3 questions from I don't know what more. There's more, but I don't know the full name. I don't know. Maybe it would be nice if you could just put in your full name there. I just read it out. Okay, so it's thank you very much for this interesting talk. I have 3 questions. How do you compare your approach to naturalistic decision making? Mustafa Zuna from KNAM. So thank you. How do you compare your approach to naturalistic decision making, like recognition primed decision making? How do you take into account errors when apparently adapted heuristics fail? And decision making is also a social process that may involve discussions, interactions. How do you take into account this point? So it's a lot. So
thank you, Mustafa. On the first question, this is about Gary Klein. Gary Klein has written a an important book, the Sources of Power, which has been reissued after 20 years, again, a few years ago. So the commonality between Gary's approach and mine approach is that he is not interested in small worlds. He's looking in the real world, which is typically a large world. And where he finds that the basic tenets of rational choice theory are not even there. For instance, in rational choice theory, you're in a situation where you have at least two options. That's a choice, or three or more. In Gary Klein's research, he finds that, for instance, firefighters, so experienced firefighters go into a situation, they are not comparing options. No, it's much like a fast and frugal tree. Based on their experience, one option comes to their mind, like going behind the place where it's burning. And he has the idea that's quickly simulated whether it works in this situation. If it works, that's being done. There's no second option. It's lexicographic again. And if it doesn't work, then there's a second one. Interestingly, the research on the fluency heuristic by us and others has shown that in experts like firefighters, or he's also concerned with military personnel, but my colleagues have done this with sports, handball players, for instance. So if you put a handball player in front, an experienced one, in front of a video with a top game and it's frozen, and ask the player, what would you do if you were the guy with the ball? And the player gives the intuitive answer. And then you leave the same video, the frozen video, for another 45 seconds and wait for more options. What you find is that the first option, on average, is the best one. The second best. The third best, and so goes down. And that gives you an idea that an experienced player or firefighter can rely on the first option that comes to mind and immediately act. And further thinking will probably only lead to worse decisions. That does not hold for a novice at all. A novice has to think. And the problem is that the so-called speed accuracy trade-off in psychology, which means that if you do something, the faster you do something, the less accurate you do, is obtained by studying novices. So undergraduates that have no idea about the problem. They are confronted, often the problem is itself made up. And this has misleadingly led researchers to think that would be a general feature. And this is an important contribution of Gary Klein's work. If you ask differences, I've written a review of his 20 years edition of the new book, and I would just, I place more effort on modeling these heuristics. Yeah? And he uses more words for these kinds. Yeah? And the moment you model them, you can identify more clearly the situation where they're ecologically rational. Okay, that was a long answer, but I think his work is really underestimated and very important. How do you take into account errors was the next one, when a heuristic fails. Now, you look again at the situation and analyze it and see to find others, so that situation may have been changed. And the third question was about the social process that involves discussions, interactions. Yes, clearly, yeah. And many, for instance, the way we have discovered heuristics comes out from an entire research group that is based, I always have had a research group where there are at least 8 or 10 people from different disciplines. So animal biology, mathematics, computer science, machine learning, psychology, economics, and so on. You get them together, and the results are really what I've presented, an outcome of collective mind. That's the normal things. And also there are many heuristics that are decidedly social, like imitation. You need something to imitate, or tit for tat. You need something to tit for tat. And these are all important processes we need to investigate and also take seriously, not just dismiss them as quirks.
So, Eva,
thank you. Thank you
like...
very much. I can show myself now because thank you very much for your answers.
Well, thank you for your question.
Thanks.
So I would like to, Eva, if I may, I would like to ask one question as well. And it is actually going back to the deep learning things that many of us do. So, for example, so I just wonder whether you would recommend using like fast and frugal trees or something like that as well for some of the notoriously difficult problems. For example, when we apply deep learning to medical data, to like brain images, it's pretty tough because it's very noisy data, and the models very often they do actually just overfit, and you have they don't generalize exactly because of the noise. And do you think that it would be helpful to look at that in a different way?
Yes. Look at it in a different way. Also, so I have worked with medical societies and doctors for over 30 years. And what they do in practice is heuristics, and mostly fast and frugal trees. For instance, heart attack diagnostic in the emergency room. And you can see the reason for that. It has to be something, a decision tree. So a fast and frugal tree is robust against overfitting. So that doesn't mean it does not overfit, but it overfits much less than complex method. It is also transparent. You can understand it. And that's very important. Doctors have to have the tree in their mind, just like the firefighters. They cannot look up things or have a computer that now does a random forest or something like that. And also being transparent enables them to understand it, and they can adapt it. So if a patient population changes, doctors can see that cue doesn't work, or it doesn't work for women as well as for men. We have to make a difference here, which they cannot do if it's a logistic regression or a neural network, God heavens. And also, finally, transparency and understandability leads to, you can teach it to others. And also, you can see discrimination much easier than with a neural network, where you only can hope that the data didn't have it, and then you don't know what to do if you find discrimination. As the Google engineers didn't know what to do when this case with the black couple came here, that just eliminated categories. So I think there are a number of advantages, and the important thing is to test this model against whatever complex model you have. And we'll often find that simplicity actually pays. But it also is a real, a revolution of thinking. We are in a society where we always praise complexity. And if something fails, we make it more complex, like the Google engineers did it with the flow. And it doesn't help them make it more complex. Our legal system is very similar. It gets more and more complex, and my tax advisor doesn't understand the tax law. Nobody can. Is this a democracy? And so the problem is much wider.
Okay, so Eva, I think we just we are past the hour. So is there any urgent questions still? So I don't think, it doesn't look like it. So nobody's raising hands. So thank you so much. This was really extremely interesting, very useful.
Yeah, it was a pleasure to talk to you.
Thank you
Yeah, it was
so much for this lecture. Yeah, absolutely.
Yeah.
So we're going to conclude now, and we will be uploading the recording of this lecture on our YouTube channel, where it will be available for anyone else who might be interested in learning more about this absolutely fascinating subject.
Yeah.
Thank you again.
Yeah.
Bye-bye.
Thank you so much. Thank
Have
you
a
so
nice
much.
evening. Yeah.
Yeah, you too. Bye-bye.